Stress in shear and torsion modulus of rigidity. Rigidity. Modulus of rigidity. So far, only the direct stresses have been considered, as these are fundamental to understanding of the basic concept of the two most commonly used design constant E and mu. There are, however, many other cases where certain shearing action taking place, as illustrated, for instance, in figure 2.1. It is clear that the rivet shown register load Q in such a manner that each total cross section is subject to transverse shearing action. An element of the rivet cut out in the forms of the rectangular block is shown with greatly greatly exaggerate displacement of the upper edge of the element with respect to the lower edge. For the case of the relatively small elastic deformations, the experimental evidence indicates that there is a linear relationship between the shearing stress tau and the distortion angles. uh, Distortion angle gamma, as shown in figure 2.1. Tangent gamma is nearly equal to gamma in radians for all small values of delta 0, and by analogy to the case of direct tensions, we can state the following general principles. G equal tau per gamma. The elastic constant G defined in equations is shown in engineering as the modulus of rigidity, or the shearing modulus of elasticity, and bears a definite numerical relations to the modulus of elasticity and the Poisson's ratio of the materials. The three basic elastic constants are connected by the following relations. G equal E for 2 multiply 1.1 plus U. Shearing stress and strains by analogy to equation illustrating axial strain. The shearing strain may be defined as gamma equals delta 0 per A. Strictly speaking, then, shearing displacement delta zero may be thought of as the angles. This concept is helpful in the analysis of torsional problems arising in machine shaft, craft, purely eccentrically loaded beams, and similar structures. The direct shearing stress in general can be computed as a shearing force Q divided by the cross-sectional area A, and for many practical applications where general spectra of gravity are involved, this approach should be entirely acceptable. Figure 2.1 pertaining to the general concept of shearing strain and stresses, given no clue as to the actual distributions of the stresses across the cross section. The first step in the treatment of any shearing problem is to define the magnitude and the directions of the external force load involved. It is assumed that the reader is familiar with the element of statics. For instance, the magnitude of the vertical shear load may be determined from the resolutions of all the external forces acting, say, on either the left or right hand portions of the beam-like component. In figure 2.1, the rivet behave as a short structural beams and Q represent the external force. Before turning our attention to some of the basic aspects of the distribution of shear stresses in beams, it is well to note that the shear stress acting on given cross-section process sliding of the transverse element. These actions provoke a response from the longitudinal fiber, which develop the complementary stress of equal magnitude to the transverse stress. This effect becomes quite apparent, for example, in loading wooden beams to destruction. Since wood is weaker along the grain parallel to the natural axis, shearing taking place among that grain. The concept of the complementary stress therefore promote the conclusion that the shearing stress must occur in pair. Analysis of shear stress distribution. Suppose that we consider an element of beams defined by the two cross sections, distance dx apart, and loaded by qm and m plus dm, shown in figure 2.2. These forces are needed for the static equilibriums of the beam element indicated. To obtain the express for the shearing stress at the layer located distance A, From the neutral axis, first consider the bending stress at distance y. S SB equal M y for I. These equations represented the well-known beam formula using by practicing design engineer. Horizontal force on the shaded element of beam cross section A B C D at the left plane A dash A dash is F dash equal my uh, b dy for I. Similarly, for the plane A dash dash A dash dash as shown, we get F dash dash equal m plus dy m plus dm yb dy for I. The net horizontal force parallel to the natural axis must be equal to F dash dash minus F dash. So equations this one and this one give these equations. Total horizontal force between y equal a and y equal h for 2 is these equations. Finally, the shear stress at y equal a is tau equal this one and this one, or this one. For the first total rectangular cross section, the shear stress can be found from this one. Give by this one by integrating between the limit of 0 and half of h. This given this one. Two important observations can now be deducted from the foregoing analysis. The shear stress distribution is parabolic for the rectangular beam across section, with the maximum value attained at the neutral axis. The maximum stress is 3.2 times the mean stress, which follows directly from equations this one.